Go through the solution for a 3-span continuous beam by using the slope deflection method. And for this purpose, I'm assuming a 3-span beam consisting of 4 supports. The left one is a simple support, constrains the beam in 2 horizontal and vertical directions. However, the other 3 supports are rollers which support the beam in just vertical direction. The span length is L and the modulus of elasticity is E, and the second moment of area is I, and a uniformly distributed load omega is applied to the whole building. I will assume some arbitrary values for these 4 parameters, L, omega, E, and I. However, for now, I continue with the parametric solution, and later on in some point, I will use these arbitrary assumptions to go forward. My desirable today is to calculate and analysis the structure to obtain support reactions, as well as shear force diagram, bending moment diagram, and the deflection of the beam. For this purpose, I'm using slope deflection method today, and later on today, I will use double integration method as well to find the maximum deformation in the span. However, in the next videos, I will solve the same structure by using other methods to validate the solution, like moment distribution method, matrix analysis, and virtual work. Today, also, I will validate my solution by using a finite element software called CSI-ETABS, and we will work it out at the end part of this video. If you're uh, curious about the finite element simulation of this beam, you can just jump to the end of the video. However, for the manual analysis of the beam, the first part of the video is of interest. So I start with the beam, and because we have 4 supports here, we have 5 reactions, as you see here. The left support has 2 reactions, as I said, because this is a simple support. The other reactions are roller support and just 1 reaction. So we know that the number of unknowns in this structure can be written like 3 times the number of members, because each member in the plane has 3 unknowns, which are shear force, moments, and axial force. So we have 3 members, 3 times 3, 9, and we have 5 reactions. Altogether, we have 14 unknown parameters. And in terms of equilibrium equations, we have 4 joints. Each joint provides 3 equilibrium reactions, altogether 12 equilibrium reactions. And as you see, they are not equal to each other, which means that this structure is 2 degrees indeterminate, which means that we need 2 more equations to be able to solve this structure. For that purpose, the more degree of indeterminacy we have in the structure, the more desirable we are to use stiffness method rather than flexibility methods. And that's why today we are using slope deflection method to solve this problem. First of all, we know this structure is symmetric, and that's why we know that half of the structure is the mirror of the other half. And in addition to that, we know the first equation, equilibrium equation, provides the summation of all forces along x should be 0, which yields to the FA, the horizontal reaction at the support A, should be 0. And just we eliminate that one, and we will be left with the 4 remaining reactions, and we know from the symmetricity that RB and RC are identical, RA and RD are identical, and for that purpose we we can say that two of the reactions are identical to the other two. And to start with the slope deflection method, we can write the free body diagram of the structure. It's like we have cut the element AB at the both ends, very close in a proximity to the supports, and we have support A at the left, support B at the right, and the element at the middle. And always we have a convention for the slope deflection in terms of the bending moments are clockwise. So as you see, I put the red bending moments clockwise, all of them. MAB means the moment at the element AB, but at the end of A. And MBA means the moment, internal moment of the element BA, which is obviously the same as element AB, at the end of B of that element. So MBC means the internal moment of the element BC at the end of B of the element BC. So practically, I'm showing you half of the structure. So you can see the dash line here at the right hand side, which shows the middle of the structure. So whatever we obtain for this half of the structure will be mirrored for the other half of the structure. The convention, when the convention for the internal moments are like the moments should be clockwise for the element, it means that they will be counterclockwise at the support. So the blue moments are counterclockwise, but their symbol is like the adjacent moment. Like when we have MAB, we have MAB blue at the left, which is the exact MAB, but counterclockwise on the support, just to comply with the equilibrium equation at the place of cut. So for the shear forces, they should be clockwise as well. And you see for the element, and you see V1 and V2, V3, they are all clockwise. They are trying to rotate the element clockwise. And when we put the red ones, we can put the blue ones in agreement with the red ones to comply with the equilibrium equations. For example, when you have V1 here, V1 blue should be here because of the equilibrium equation. They should be identical but in the opposite direction. So always the blue ones are in opposite direction of the red ones, and the convention I'm talking about are always valid for the element, not for the support. Support convention is opposite the convention for the element. So these are the forces we have in the element. However, we don't show the axial force here because it's a beam, and most likely the axial force is zero or very negligible in practical cases. However, you can show the axial forces in here, but at the end of the day, it will be either zero or will not influence your method because you're writing the other equilibrium equations. So to start with the slope deflection method, we should know that for each element like AB, we can write two equations for the slope deflection solution. The first one is this one, and if you understand the first one, the others will follow the same pattern of this one. For example, for element AB, I'm writing the MAB, the moment at the end of A of element AB is equal to 2EI over L. E is the module of elasticity, and I is the second moment of area, and L is the length of the element, 2 theta A. Theta A is the rotation of end of A of element AB, plus theta B, which is the rotation of the point B of the end of element AB or BA, minus omega L squared over 12. This last term is called fixed end moment, and it's a function of the applied external forces. And because I have a uniformly distributed load here, omega, I will come up with omega L square over 12 here. If the external force is different, so you will have different terminology here. However, I will go to the next slide later on. I will show you how does it work for different kind of external loads. So bear with me and don't worry about the last term here. If you if you swap the A and B places in this formula, you will come up with another formula, another equation here, which goes for MBA, which MBA is this M at the end of B of element BA, and it would be 2 EI over L times 2 theta B plus theta A. Just swap the A and B. And here we have plus fixed end moment. So the fixed end moment should be the right end fixed end moment. So we will have two fixed end moment at the left and right of the element. So we come up with two equations for element AB. We can follow the same pattern for element BC, which is this element at the right hand side. You can just see half of it, but the left part is MBC, the right part is MCB. So, and it will be written around versus theta B and theta C, and the fixed moments are the same because we have the same external load on element BC. And for each element, you can write two equations of slope deflection. So because we have three elements, you can write 3 times 2 equations, but I'm concentrating on only half of this structure, and that's why I'm writing these equations for A, B, and BC only. But you can obviously write the same equation for element CD. In these equations, in the right-hand side, you have three distinct unknowns, like theta A, B, C. The other things are known. And from the symmetricity, you know that theta C and theta B should be like theta C is minus theta B. Otherwise, you can get the symmetricity in the deformation shape of the structure. And when you write these equations for the slope deflection, you should combine them with equilibrium equations at nodes. So for example, at node A here, you can write equilibrium equations like MAB should be equal to 0 because you don't have anything other than MAB, and you're writing practically summation of M over point A is equal to 0. So you come up with this equation. And at node B, which is here, in this area, in this section, you should write summation of M should be 0. You have two M's here, MBA and MBC. So the summation of MBA and MBC should be 0. So you have two equations from equilibrium and four equations from the slope deflection here. All together, you have theta A, B, C as unknowns, and you have these two equations and this equation here. You can substitute all of these equations here in the equilibrium equations along with the symmetricity equation, and you can solve a 2 by 2 system of equations, and you can come up with theta A and theta B, as you can see. So when you have theta A and theta B in hand, you can put back them into these equations of slope deflection, and you can calculate all of the M's like MAB, BA, BC, and CB. And if you do that, you will come up with these values for different internal M values. And if you have M values here in these sections, you can calculate easily the shear forces by writing equilibrium equations for the shear between shear and moments. Like, for example, here you can write MAB plus MBA plus V1 times L is equal to 0. So you will come up with V1. And if you write here in this section, if you write summation of Fy equal to 0, you will come up with V1 equal to V2. And uh, V1 plus or V1 equal to V2 plus omega times L. So you have omega as well. So uh, with writing, with having the internal moments in hand, you can come up with calculating the shear forces at the end of all elements. So if you have shear forces at elements, you can calculate the support reactions, like RA is equal to V1, because this summation of Fy along all forces here should be 0. So RA is identical to V1, and for example, here you can write summation of Fy equal to 0, which gives you RB plus V2 will be equal to V3. And for this part, the omega doesn't play any role, since you have just cut at the element like an epsilon, very close proximity to the support. And not last not least, you have some formulation for the fixed end moments. If you remember, I told you the last term in the slope deflection equations are fixed end moment, and if you go through the structure analysis books, all of them have a table like this. This is coming from Hibbeler book 2006, which gives you the fixed moment at both ends of the element. Like here, if you have uniformly distributed load on a beam like L, we're having L length equal to L, the left fixed moment will be omega L2 over 12, and the right hand one is this one, but they are positive, as you see. But in our case, we used opposite direction of this moment. That's why we used minus omega L squared over 2 at the left of the equations, and we use the positive value at the right end of the equations. So if you have a different external load, you can use this table as applies. So here we just move to the numerical solution, because we cannot forward to the other purposes without using values, actual values. For now, we had everything in parametric solution. Now we assume those assumptions: L equal to 5 meter, omega 20 kilonewton over meter, the module of elasticity 210 gigapascal, representing S355 steel material grade, and the second moment of area is like 63,720 centimeter powered 4 for representing HE 450A section, steel section. So if you use these values in the previous slide formulas, you will come up with the values for theta A and theta B. Support reactions will be 40 kilonewton and 110 kilonewton. Bending moments are like this, and the shear forces will be these values. So we just moved from the parametric solution to the numerical solution by using some arbitrary values for the input variables. And the next slide goes to show how we can draw the moment diagrams and shear diagrams. And for that purpose, I've the structure here again, the whole structure, and we have a symmetricity dash line at the middle. So if you remember, we had the shear forces like V1 was 40 and V2 was minus 60. And if you take a look at the V1 is here, V2 is here, and they are rotating the element clockwise. And when you want to draw the diagrams for the shear and moment, you should be you should note that the conventions are a little bit different from slope deflection method, because bending moments should make the beam bottom in tension, and shear forces should rotate a member clockwise. So the convention for the shear forces is the same as the slope deflection convention. However, the bending moment convention is a little bit different. The bending moment convention for the slope deflection was clockwise. However, here is different. The bending moment should make the bottom of the beam in tension. So you should be careful about that. Uh, for the shear force, there is no difference. So we can use the values. We have 40 and minus 60 for the AB. So we have 40 at the left and minus 60 at the right. And we can just connect these two values by a line. And that's why, because when you have a uniformly distributed load on the beam, which means constant, it's a constant value, the shear force diagram will be linear, and the moment diagram will be uh, in terms of polynomial uh, of 2, like x2. And that's why always it's like we are going through omega to v and through m, like having an integration. So if we have a constant here, if we integrate, we will come up to a linear function, and from a linear function, if we integrate, we will come up to the polynomial of grade 2. So for now, the shear force is linear because the external force is uniformly distributed. And for the BC, we have 50 and minus 60. Again, we connect them with a line, and the the right half of the structure is the mirror of the left half because of the symmetricity. And if you go to the moments, it's a little bit tricky because the convention, as I said, the convention here for the bending diagram is a little bit different from the slope deflection convention. And here you should be aware that the moments are coming from the slope deflection analysis, which moments are like this, clockwise. But here in the conventions of moment diagram, we should be noticing that the bending moments make beams bottom in tension. So for that purpose, MAB is fine, which makes the beam bottom in tension, but M MAB is fine, but MBA is not fine. MBA should be opposite of this. So I make it opposite and I say MBA is minus 50. Okay, so when we have MBA 50 kilonewton, this MBA, we can say it's opposite direction and minus 50. So when we want to draw the moment diagram, we should go from 0 for MAB to minus 50 for MBA and connect these two by a polynomial of grade 2, like x2, x squared. And we have two ways of drawing this, like this one or like having like this one. And we choose this polynomial because the concavity of we have two ways of connecting these 2 points together. One is like this, and the other is like this. And we choose this one because we know that when we come from the shear force to the moment diagram, it's like integration. And vice versa, when we go from the moment diagram to the shear force diagram, it's like getting a derivation. And here you can see the derivation of this diagram should be positive, which is, and here the derivation of this diagram in this region should be negative, which is. So based on the derivation, derivation of this diagram, which is the shear force value, you can come up with the correct form of the bending moment diagram. And you can continue with the rest of the bending moment diagram by having minus 50 here and connecting these two like this, because again, in this region, the derivation of the moment diagram is positive, and in this region, the derivation of moment diagram is negative. And as I said before, the right-hand side, the left right-hand side of the structure is the mirror of the left of the other part, which is the left-hand side. And this is the deflection of the beam, and I will demonstrate it by using ETABS software to see how we can model it in a finite element software. And you can realize that from omega, if you make an integration from omega, you will go to the shear force diagram. If you make another integration, you will go to the moment diagram. And if you do two more integrations, you will go to the deformation shape of the beam, as you can see here. And we will do it via the integration method in the next slides, because the slope deflection is only able to provide you with the internal forces and the deflection only at the nodes, and uh, it's very difficult to employ the deflection method if you want to, for example, come up with the deformation at the middle span or at some arbitrary points of the beam. So for that purpose, we will use another method, which is double integration in the next slide. However, before that, I want to just show you that I have used a CSI-ETABS software as a finite element modeling software to validate my calculation, and the diagrams for the internal shear and moment forces are validating our hand calculations, as you can see here. And the deformation shape we obtained is like this. For example, theta A is a 0.000467, and theta B is minus 0.3771155 radian, and this is positive and this is negative, which means that, for example, for point A, the theta A is clockwise, which is positive, and for theta B, the theta B is negative, which is the angle between the undeformed shape line and the deformed shape line, and at node B. So this is counterclockwise, and theta A is clockwise. It's worth noting that the manual results might be slightly different from whatever you get from the software, from the finite element software, and that's because in the manual calculation of the slope deflection method, you're just considering the flexural stiffness. However, when you use the software, you're just using both flexural stiffness and shear stiffness, and the difference comes from the accounting for shear stiffness in the finite element method, rather than eliminating that shear stiffness in the manual calculation. Besides, you can set the shear stiffness in the finite element to 0 to see how they will be identical. We just forward to use the double integration method for calculating the deformation shape of the whole beam as a function, and for that purpose I'm using the AB segment of the beam. This is the segment AB of the beam from A to B, and we have an external omega distributed load on the beam. The shear force at the both ends are these values, and the moments at the left end is 0, at the right end is omega L squared over 10. And the purpose is to calculate the function of the deformation of this segment of the AB. For that purpose, I make cuts of this AB at an arbitrary place, like uh, X position from the left end. So at the left end, X is 0, and here X is X. So I want to calculate the internal shear force and internal moment at an arbitrary X cut section. So again, for the conventions, we are using the conventions that we use for the shear and moment diagrams, like bending moments should make the bottom of the beam in tension, and shear forces should rotate the element like clockwise. And for that purpose, we go to the equilibrium equations, and we can write the summation of moment should be 0, and we can calculate the function of mx, which varies versus x. X is 0. If x is 0, it should be 0, and if x is L, it should be omega L squared over 10. So this is the function of moment, internal moment along the element AB. And when we have the internal moment function, the internal moment function is always equal to EI times the second derivation of a y. Y is the deformation function along the AB element. So this is a partial differential equation that we wish to solve, and for that purpose we just replace the mx here, and you will come up with EI. The second derivation of y will be this function here. And if you once perform the integration over this equation, you will come up with the first derivation of y, and if you apply a second integration, you will come up with the function of y itself. So when you proceed with this function, which is this, it is x squared. So if you do a single integration, you will come up with x cubic here, and one constant appears here, and if you do an extra integration over this function, you will come up with x4 here, and c1 comes here, c1x, and another constant appears here. So that's why this method is called double integration method, and you will come up with two constants here, c1 and c2. And if you want to calculate the C1 and C2, you need to go back to the boundary conditions, which are usually in the supports. As you can see here at node A, I have the condition like at at x0, the y should be 0 because it's a support at node A, and at the x equal to L, y should be 0 because it's a roller support at node B. So with these two conditions, we can come up with C1 and C2. And if you calculate C1 and C2, this will be known, and this is the deformation shape of the beam in AB segment. And you just replace the C1 and C2 here, and these are two equations. This is the function of the deformation of the AB segment, and this is the function of theta, the rotation of different nodes at segment AB. So with this in hand, we have the variation of function yx for the segment AB, and we can draw the function like this by just using some arbitrary values for x between 0 and L, and you can come up with the shape of the exact shape of the deformed shape of the segment AB between x0 and L. However, for the slope deflection method, you couldn't come up with the calculating of the maximum value of the deformation, or it was not really easy to do so. However, here, because you have the deformation function of the whole segment, it's very easy to calculate the maximum y here. And for that purpose, I want to calculate the maximum of the yx. And for that purpose, you can just set the derivation to 0 to calculate the relative um, maximum value of the function. So for that purpose, the derivation of y versus x should be 0, and this, you should solve this equation here. However, this is a cubic equation, the polynomial of grade 3, which is not very easy to do so. However, if you set the values of L and omega into the equation, you need to solve this one, and you can do it very easily by using Excel. And I'll show you how you can use the goal seeker in Excel to come up with these three roots of this equation. So you have that basically the problem is you have this equation to be solved, and I just go to the Excel to see how we can solve this equation. So I just use this equation here to put it here in Excel. Assume that x is this one, and I will change this for now, just set it to 0. And if my x is here, this is the equation that I was talking about. 1 over 6 b1 cubic. b1 is my x, so x cubic plus x squared minus 25 over 8. So this is my equation of interest to be 0. I want to set this to 0, but I don't know which x makes this equation to 0. So for that purpose, and I just put the equation of yx here for later on to see how y would be. For that purpose, there is a fantastic option in Excel if you go to the data, and if you go to forecast and what if analysis. And in what if analysis, if you go to the goal seek, so from the data menu, go to the forecast, then what if analysis and goal seek. And here you will have this window which tells you which cell you want to play with. I will say this cell, please, enter. And to value, oh, sorry, I want to play with this cell to be 0, and by changing this cell. So it means that by changing b1, which is my x, to set the b5, which is my function, to 0. So, okay. And it goes to change the different values of the x to come up with a 0 value with this. And you can see it's minus 4 times 10 powered minus 5, which is practically 0. It's very close to the proximity of the 0. So one of the roots is 2.23 here. You can come up with the other roots, like if you go here and again you go to the forecast, what if analysis, go seek, and say, sorry, if we start with something like 20, you can start from 0 or 20 or minus 50. I mean, from different points, it approaches to different routes. And if you go to the forecast, what if analysis, go seek, and you say, I want this cell to be 0 by changing this cell, and you press OK, it calculates the value of x is equal to 5 plus 5.34 when this is almost 0. So if you do this from minus 20, you will come up with a third root, right? Minus 1.57. So if I get back to my presentation again, basically you have three roots for this equation. However, only one of them is valid because the other two are outside the context of 0 and 5, because x can go just from the 0 to 5. You can see here x is between 0 and L is 5 meters. So this is out of the game, this is out of the game, and you have only this root. So for this x, you should calculate this function y, and you will come up with y equal to minus 0.643 millimeter. And this is the maximum value, the absolute maximum value of the deformation function. And if you go through your finite element simulation by using the software, you can see the software gives you minus 0.644, which is just one precision in the third precision different from your manual calculation. So it means that they are in very good agreement, and it validates the hand calculations. So in this point, we have done the analysis of this beam by using slope-deflection method. Again, validate the results by using the double integration method. And now we move to see how we can simulate this in the finite element software by using CSI-ETABS. Thank you for this part, and we will move to the next part of the video. So I'm using CSI-ETABS, and if you go to a new model to create your model of continuous beam, first of all, you need to set your display units to SI. I'll do so. And the rest of these are not important because I'm not going to use any design feature here, and I'm using just the structure analysis. However, if you're interested in the design, you can set the other sections to your desirable design code. And I'll go with the grid line only, and I will go with 4 grid lines, and I will go with 5 meter and number of story 1, and grid lines in X direction and Y direction, and the spacing 5. You can skip this part and set it by yourself later on, but it's easier for me to do it here. And if I press OK, I have a grid line here. All of the dimensions are 5 meters, so I will use one of the planes to set up my desirable structure. So I go to the left hand window, and I will go to the elevation A, for example, which is YZ. I can create my beam here, or I can go to the elevation 1 and I work in XZ. So it's either in this way or this way, both are fine. And here I start by using a or draw an element like beam element, okay, and I can use either of these like quick draw, and here one beam, 2 beam, 3 beams here, and then I will select this point and I will assign joint restraint, and it's like closed in everything, not rotation, just a simple support. Press OK. And for the rest of nodes, I will assign them to restraint, but here I wanted them to be closed in translation and direction, but they should be free in X translation, which means they are roller, aren't they? So they are closed in Y and Z direction, and they are free to move in x direction. However, in terms of rotation, they should be rotating only in the y-axis, and x and z axis rotation should be closed because we are working in the plane, in the xz plane. So I just close x and z rotation for them, and I forgot to do so for the first one. Again, I go there, I assign the restraint. Although for the first one everything is closed in translational, but it should be closed in x and y rotation as well. So only the point A is only free to move in the rotation of a y-axis. So I press OK. So I have the geometry and supports for my beam, and so I go to define my material section. I go with 4000 psi. This one you can create and add your own, but I can use from this one. I just set the density of the material to 0 because I don't want an additional load to be imposed as a self-load to the structure. And this should be 210 gigapascal, so it should be 210,000 megapascal. And I press OK and press OK. This is my material. I go to define section property, and a section, I need a section for my beam. I will add a new section property, and I will use a general section like here, and I'll use a general section like, I name it my beam, and the material would be 4000 psi, and these doesn't matter, but here I can put my own values here. I'm interested on this one only because I have 63720 as my second moment of inertia, which mostly contribute to the bending moments of my beam. So I press OK, OK. I select these three beams and I assign them to the frame section property my beam. So I just created my beam in the previous menu, and then now I assign them to my beams. So right click on one of them and you can see it's the property is my beam here, right? So I have my beam here. So the remaining thing is to assign everything like a distributed external force, and it should be a uniform distributed load like 20 kilonewton over meter over all of the beams. So it goes to the dead load case here, and I press OK. So I have 20 kilonewton uniformly distributed for all beams. If you right click on any of them, any of the beams, you can see it's here, 20 kilonewton over meter. Now you can run your model, and for that purpose I need to save my model somewhere, and my beam is the name of my file, and I just save it and I start analyzing the beam for the applied load. And it takes a couple of minutes or seconds, and then I will compare the results with what I've received from my manual calculation. But just to remind ourselves that the diagrams for the shear forces and moments diagrams can be compared with the results of of this analysis, and also you can compare the theta values at both ends, etc. So this is okay because it says that for the modal analysis there is a problem, but I don't need to go for modal analysis because I don't have a mass here. You can set the modal analysis to not to run and avoid this warning. And here you can go to show the deform shape of the structure, and for that purpose, for the dead load case, you can press OK, and you can see the deformation shape of the structure. And if you go on this point, you can see on the right click, or you don't need right click, and if you go on that, you can see the rotation of RY for node A is 0.300468, and this is quite comparable to the value we received. So they might be a little bit difference between these two, the finite element model and the hand calculation, and that's because when you define your section property here, this is my beam, and I just changed the second moment of inertia here. However, you have AS2, AS3, the areas which contribute to the shear forces. And if you want to eliminate shear forces, one way to do so is to use a large value of for these values AS2 and AS3, and they will tend to um, to to produce a very low shear deformation, and you will get only the flexural deformation. So this is out of scope of this video. I will try to elaborate about the shear deformation in another video to explain how the relationship between the flexural deformation and shear deformations would be. But in this case, you can go through here to see how the moment distribution would be, or how the shear distribution would be. Sorry, shear 2 is the major shear, and you can compare these values with your hand calculation, and any other stuff like the reactions or any other structural output can be compared to the manual calculation, and this is a way to validate how precise your manual calculation is. I hope you have enjoyed this video, and thank you for